Hi, this is week 35 of AP Physics, and we're starting Unit 10, which deals with mechanical waves and sound. For our agenda, we'll be looking at properties of waves, Part 1 and Part 2. And for our lesson objective, students will learn about the different type of waves as well as the relationship between frequency and wavelength and how they affect the speed of a wave. Let's go ahead and get started.
Let's begin with properties of waves. A wave is a traveling disturbance that transfers energy and momentum as well. Mechanical waves are those which require a medium. Mediums include examples such as sound waves, water waves, or a wave traveling down a road. Now, a medium is a substance used to propagate the wave. Again, air is an excellent example. Water and solid objects also could be mediums for the wave. The propagation of a mechanical wave depends only on the properties of the medium. So for example, the speed of a sound wave in air versus the speed of the same wave in water will have different velocities because they have different mediums. If there is no medium present, then that wave will not propagate. For example, sound cannot travel through a vacuum when there's no air present. An electromagnetic wave is one, like for example, such as light, does not require a medium. A mechanical wave includes transverse and longitudinal waves. For transverse wave, the disturbance is perpendicular to the wave motion. So for example, in the picture at the bottom of the slide, you see the hand motion is both up and down, but the wave motion is to the right. So they are perpendicular to each other. On the other hand, a longitudinal wave is one with a disturbance that is parallel to the wave motion. So in the picture at the bottom, you can go ahead and see the hand moving forwards and backwards, and that's going to go ahead and create a longitudinal wave. The wave pulse is a single disturbance. A periodic wave is a wave that occurs in regular intervals, and a standing wave is a combination of two waves moving in opposite directions. Now, let's go ahead and take a look at this diagram for part of a wave. Now, the top of the wave is referred to as the crest. Now, the wavelength is the distance from one crest to another. Now, the wavelength could also be the distance from the bottom of the wave, which is also referred to as a trough, to the next trough. Now, the amplitude is the distance from the equilibrium point down to the top of the crest or the bottom of the trough. The highest point on the wave is called the crest. The lowest point is called the trough. The maximum disturbance of a wave moves above or below the equilibrium point is called the amplitude. The amount of energy of a wave depends on the amplitude. The distance between two successive waves is called the wavelength. The symbol for wavelength is lambda. It looks like an upside down Y. It's really Greek letter L, and it's measured in meters. The number of waves per second is called the frequency, symbol is F, measured in hertz. The amount of time needed to complete one complete wave is called the period, symbol is T, and it is measured in seconds. The speed of the wave is measured using the formula V is equal to delta X over delta T, so it's the change in displacement over change in time. The frequency of the wave is found using the formula frequency equals 1 over t, so frequency is the inverse of the period of a wave. And finally, the speed of a wave can also be measured using the following formula, V equals F times lambda, which is velocity is equal to frequency in hertz, multiplied times wavelength in meters. Now let's go ahead and solve some examples.
In example 1, we're asked, a wave is traveling in the positive x direction. Find the wavelength, speed, and period of the wave if it has a frequency of 8 hertz and the distance delta x is equal to 40 centimeters. Now here you can see in the diagram, delta x is the distance from the crest of one wave to the crest of another. So that is actually the wavelength. So our wavelength is delta x, which is 40 centimeters, which is given right here, and in meters, 0.4 meters. Next, they asked us to find the speed of the wave. For the speed, we're going to solve it for it this way. It's going to be lambda multiplied times the frequency. So the wavelength multiplies times the frequency. Wavelength is 0.40 meters. And the frequency, it is 8 hertz. Alright, so we go ahead and multiply both of these and we end up with 3.2 meters per second. Next, they want us to go ahead and find the period of the wave. Now the period is the inverse of the frequency. So it'll be 1 over 8 hertz. So that's going to go ahead and give us the following. 0.125 seconds. That will be the period of the wave. Alright, so that is example number 1. In problem 1, they asked us, is the frequency of a wave affected by the wave's amplitude? The answer, no. The amplitude does not affect the frequency of the wave, though a larger amplitude would mean that the wave has more energy, but again, no, the frequency is not affected by the amplitude of the wave. In problem 2, we're asked, a wave traveling in the positive x direction, find the wavelength, speed, and period of the wave if it has a frequency of 15 hertz, and delta x, which is the distance between the two crests, is 72 centimeters. So we know that the wavelength is going to go ahead and be same as delta x, the distance between the two crests, so which is 72 centimeters, but we normally want those in meters, so divided by 100, so it's 0.72 meters. Next, let's go ahead and find the speed of the wave. So speed will be velocity equals lambda times frequency. So lambda, which is a wavelength, is 0.72 meters, and we're going to multiply it times the frequency, which is given to us, which is 15 hertz. And if we multiply both of those, we go ahead and we get the speed of the wave. 0.72 times 15 gives me 10.8 meters per second. Next, they want us to go ahead and find the period. For the period is the inverse of the frequency. All right, and our frequency is 15 hertz. So that goes ahead and gives us 1 over 15. It is 0.067 seconds. That will be the period of this wave. Next, let's go ahead and take a look at example number 2. In this one, they ask us, a wave has a wavelength of 3 meters. Calculate the frequency of the wave if it is A, sound wave, and B, what if it's a light wave? Alright, so we're going to go ahead and use this formula. So the velocity is equal to lambda times frequency. Alright, now the wave has a wavelength of 3 meters, so that is given to us already. So wavelength is 3 meters. Now, first of all, we're going to treat it as a sound wave. Now, sound wave, the velocity of sound is 343 meters per second. So for part A, we want to go ahead and figure out the frequency. So we're going to go ahead and modify the formula slightly. So it's going to be V over lambda. Alright, so that is this formula modified. So frequency equals velocity over the wavelength. So the velocity for sound is 343 meters per second. And lambda, it is 3 meters. So all we have to do is go ahead and divide, and we get our answer, 343 divided by 3. So it gives us 114 hertz. Now, what if the wave, instead of being a sound wave, is a light wave? Now we go ahead and solve for part B, same formula, but the velocity is going to be different. 3.0 times 10 to the 8 meters per second is the speed of light, and the wavelength is still 3 meters, so it's going to give us 1.0 times 10 to the 8 hertz. So that will be the frequency for part A and part B of example number 2. Next, let's go ahead and move along. In problem 3, they ask us the following question. It says, a wave in one medium encounters a new medium and enters it. Which of the following wave properties will be affected in this process? Alright, so the speed of the wave will be affected because the medium determines the speed of the wave. So if you have a different medium, if we're changing the medium, we're going from one medium to a different medium, that will affect the speed of the wave. So C. Also, those waves might be spread out or maybe more compressed, so the wavelength will be affected as well. So the speed and the wavelength, but not the frequency. In problem number 4, they ask you find the wavelength of an electromagnetic wave with a frequency of 9 gigahertz, which is 9 times 10 to the 9 hertz, which is the microwave range. Alright, so let's go ahead and do that. So we're looking for wavelength here. formula, it is this. And again, we're looking for wavelength. So we're going to modify it so it looks like this. Wavelength is equal to velocity over the frequency. Now, it is an electromagnetic wave, so therefore it goes at the speed of light. 3 times 10 to the 8 meters per second. That's velocity for the speed of light divided by the frequency of 9 times 10 to the 9 hertz. And that's going to go ahead and give us its wavelength. So it's going to be 3 times 10 to the 8 divided by 9 times 10 to the 9. Gives us a wavelength of 0.033 meters. Alright, that is part A. In part B, they ask you, find the speed of a sound wave in an unknown fluid medium if a frequency of 567 hertz has a wavelength of 2.5 meters. Alright, so for that problem, we'll go back to this formula because we want the speed, and they give us both the wavelength and the frequency. For the wavelength is 2.5 meters, so we're going to go ahead and put that in, 2.5 meters. And the frequency, it is 567 hertz. So we just multiply both of those. And we get our answer, which is 1,400, and we'll round it off to 18 meters per second. Alright, so that'll be our answer for part A and B of problem number 4. Next, let's go ahead and move along to problem number 5. It says, students use a speaker connected to a sine wave generator to project a sound wave into an open end of a tube that is closed on the right end. The speaker is very close to the tube. A sensor is used to measure the pressure differences created by the sound, and the results are displayed on a computer. The entire apparatus is in a sealed chamber that can be filled with different gases. The student varies the frequency of the sound unit until the maximum loudness from the tube is achieved. The graph above represents a computer display of gauge pressure, the amount by which the pressure is above or below the atmospheric pressure as a function of time. What is the amplitude and frequency of the wave? Alright, and we're giving all of this. Now here we have the equilibrium point right down the middle at 0. And they want to know the amplitude. So notice the amplitude pressures in pascals is going to go all the way to 0.04. So it is from the center point up to the crest of each of the waves. So it is 0.04. So our amplitude is going to be 0.04. So it's either A or B, definitely not C or D. Now let's go ahead and find the frequency. Frequency is found by getting the inverse of the period. So the period is the time to complete one loop. So the wave begins here, goes up, down, and completes it right here. It takes a 0.01 seconds. So that is the period. So our answer will be the inverse of 0.01 second. So that's going to go ahead and be 100 hertz. So our answer is the letter B. The pressure is 0.04 pascals and 100 hertz. That will be the answer for this question. For our next question, they ask you problem 6. In the figure 1 above represents atoms in a solid material. A particle hits atom P and the atom vibrates, disturbing nearby atoms. Figure 2 represents just the vertical and horizontal rows containing atom P and shows the propagation of the disturbance along them. So which of the following statements correctly indicates the direction of atoms P's vibration and the type of vibration along each row? Alright, so there's atom P right there. It is hit, and now you get this type of waves. So looking at the waves again, so going down, let's go down. So vertical, notice that the atoms are colliding against each other. That will be a longitudinal wave. So it's either A or D as our answer. And then to the side, horizontal, that is a transverse wave. So therefore our answer for this one will be letter A. Next, problem 7 says a transverse periodic wave travels along a string that is stretched along the x-axis. The figure above shows the vertical position of a point on the string as a function of time. What is the amplitude of the wave? So here we have it, the amplitude of the wave, again from the middle part, the equilibrium point, to the top of the crest. That's what you measure. So it's 1, 2, 3, 4, 4 YO. So the answer for this problem will be letter B. And now problem number 8 says, the figure shows a portion of a periodic wave on a string at a particular moment in time. The vertical rows indicate the direction of the velocity of some point on the string, if the wave's moving to the right or to the left. Alright, so here we go. And in this diagram, you go ahead and you take a look at it. And let me go ahead and do a quick drawing of it. And see, we have this point, and here, there, and there as well. Alright, so it's moving to the left, it's moving to the right, neither direction, either direction. Alright, so now let's take a look at the arrow. We have an arrow, we're going to draw the arrows going up, and this one's going down, down, up, up, and down. Alright, so what we could do then to compare them is just draw another line that is more or less touching the arrowheads and matching it. So it'll look kind of like this. See, I'm touching the arrowheads. Alright, and as you can see, my blue wave is to the left of the original. So therefore, the answer will be letter B, to the left. This brings us to the end of our lesson. Thank you so much for watching.